Hi folks, Buckley here. Welcome to lecture number 16 in MEEG102. Today we're going to talk about auxiliary views, a little bit about advanced dimensioning, and we're also going to talk about product safety. A few reminders before we get started. First, exam 2 is coming up on Thursday, the 30th of April. Review materials are going to be released today, so it's a good time to get started on that. Online labs, online lab number 7 has started this week. Some of you are already done with your Tuesday lab, and some are just going into it on Thursday. You only have one lab left after this. This is we have 2 weeks for this lab, and then and the assignment that's associated with it, and then we'll have one more lab. Individual assignments. Assignment number 5 is due this week by 5 p.m. the day of your lab. So if you're in the Thursday section, it's due by 5 p.m. today. If you were in the Tuesday section, it was already due. Assignment number 6 is assigned. It opens up in your lab section today. You have 2 weeks to complete it, and it'll again be due by 5 p.m. the day of your lab in 2 weeks. Assignment number 6 is the last assignment, okay, last individual assignment. So one more lab, and then finishing this individual assignment, and then you are done with that. Okay. The remainder of the class is going to be largely dedicated. We have a couple weeks left to the design project and helping you guys finish that out. So what you're doing right now on the design project starting this week is working on milestone number 8, detailed engineering design. Okay, so that should be what you're focused on for the next 2 weeks. All right, live sessions with me. So those are optional, but they're recommended. Okay, Tuesdays and Thursdays for a half hour, 10:30 to 11. We can talk about your project. We can talk about your labs, your individual assignments, or the content of any of the lectures. See Canvas for your Zoom link. Honors, you should be working on your maker profile. All right. Let's start with a class participation. Okay, so this is an individual activity. Please solve it on your own on a piece of paper. See Canvas for more details. I've also posted to you the necessary engineering fits tables. Okay, so solve this on your own, scan to PDF, and upload to Canvas. Standard, straightforward engineering fits problem. Okay, that'll be due by noon today. All right, so I want to first talk about auxiliary views in engineering drawing packets. I'm going to start by just reviewing again what are the essential items in an engineering drawing packet. So this is our very, very simple block and shaft problem, 2 blocks and a shaft that we're putting together into an assembly. So we'd expect to see the assembly, the exploded assembly, and dimension parts. The elements that we're looking for, we'll be looking for in your engineering drawing packets. And also you should look for in other people's engineering drawing packets are part lists and callouts, details on any mates, and then making sure that things like materials are specified in the title block. So let's run through this real quick. Okay, so our assembly drawing is first in the packet. I've got callouts that are showing where those parts are, and they're being tied to a parts table. The bond between these 2 blocks here is specified, so that's going to be glued, fully bonded surfaces with cyanoacrylate glue or crazy glue, okay, and that would be a completed assembly drawing. Next up would be the exploded assembly. So on the exploded assembly, I still need to see part callouts. It is recommended that you also include the lines that go with an explosion view, okay, so that actually show where these parts are going. Obviously, this one is very simple, but in more complicated parts, it would be helpful to have this, okay. So second is exploded assembly, and then we go one by one through the parts. Notice that these are fully dimensioned drawings, okay, just like we've been practicing in the first part of the class, but I'm also making sure to specify what the material is there. Okay, so that's the block. I have 2 of those, quantity 2, and then the shaft, that's going to be made from wood, and I have 1 of those. So that would be a completed drawing packet. These are very, very simple parts, okay, so I don't really need anything other than assembly, exploded assembly, and then my parts drawings in order to communicate it. Both the assembly and the parts are pretty straightforward. But that's not always the case. So in some instances, either your assembly and or the parts themselves are kind of complicated, okay, and some additional information could be communicated to your manufacturer to make it clear, okay. So an example of this would be your rubber band shooter, which you're working on right now in both MEEG102 and MEEG104, okay, and there's some things with this that really, if you think about it, would make it difficult to fully convey to somebody who's manufacturing this design all of the intricacies of the part if we just went with what you just saw with our simple block and shaft problem, right? So we could really use, first thing is that the part itself, so the casing for the barrel or for the body of the shooter there, is obscuring some of the interior parts, namely the chamber and the trigger, and any type of pins or fasteners that are being used in there to hold them in place are obscured by the casing of the body of the shooter. Okay, so it would be helpful to see in an assembled form to see where these components are. Okay, and we're going to use a special view to do that. The second thing that's going on is those parts themselves, particularly the chamber and the trigger, are highly detailed parts. There's a lot of detail on them that allows them to function properly and also allows it to hold the rubber band, right? So those are highly detailed parts that it may be difficult just with a standard orthographic projection and an isometric view to communicate what's going on with those parts themselves. So we have some additional detail that's going to need to happen on the assembly, and we have some additional detail that's going to need to happen on the parts themselves. So let's walk through this. Okay, so section views and broken out section views are used. They can be used on both parts, so individual one item parts, the engineering drawings for those, and also on assemblies to show internal components or dimensions that are otherwise obscured. So let's start with a part. Okay, so this is the trigger. This is my drawing, or I'm sorry, of the chamber. This is my drawing of the chamber. Okay, and you'll see that we have a section view here. Section BB is as if we cut through. We're going to cut through the chamber right along this axis marked BB, and then we get to see it in cross section. Okay, so this would be a section view on a part that gives us the shape, right? This is very easy to now see the shape and exactly where these interior holes are placed. Okay, so that makes for a nice section view there on the part level. Section views can also be done on the assembly level to show internal components that are otherwise obscured. This is what's called a broken out section view. So the difference between a straight up section view and a broken out section view is broken out section views can cut away just a little chunk. Okay, so instead of taking, like, I don't know, a slicer and slicing all the way across this design, you're just cutting away one little bit here, okay, to see these internal components. So any hatching that you see on any of these, that conveys that you've made a cut. Okay, so that's important, and SolidWorks will do that for you automatically. It'll make that hatching whenever you do a section view or a broken out section view. Okay, but broken out section views only take away a little chunk. They don't go completely across the part. But that broken out section view very nicely shows the location and the orientation of those interior components relative to the body of the shooter. Okay, so a broken out section view would be good on the assembly there. All right. Detailed views are a special kind of view. It's basically like holding up a magnifying glass to your part. It can be done at the part level and it can be done at the assembly level. Okay, so all of these views work on either parts or assemblies. I'm going to show you an example of a detailed view here that was used. So this is again my drawing of the chamber. There is a lot of detail on these little teeth on the chamber. So they have a little bump here that's used to secure the rubber band. So the rubber band sits here. This little bump keeps it from sliding off until it's ready to fire. Okay, this type of angle, so these are specifically radiused, all of that. That's a lot of detail that would be difficult to convey at this scale. So this is the scale at which it's good to talk about the bolt circles that you see here. Okay, maybe the outer dimension, okay, the inner dimension, but it would be tough to give detail on all this little fine point here. So what we do is we basically hold a magnifying glass up. So this designation here, C, okay, is a detail view of just this piece, and we would get a little through our magnifying glass, we would see this. This is in 4x scales, 4:1, okay? And I can now see things that allow me to very cleanly describe them on the drawing, right? So all of this detail would be lost at this scale. I blow it up and I slap it on the drawing. And I'll show you where it's located on the drawing in just a second. Remember, I've given you the chamber drawing, but I do need you to make your own for the trigger, okay, which is another complicated part, as well as the drawings for the barrel, for the pins, and for the body of the rubber band shooter. Okay, those are a little simpler. All right, so let's go through now. We're going to go through a engineering drawing packet that's actually quite good. It's missing a few things, and we're going to practice calling out what might be missing on this. Okay, so this is a previous student's work. They did very well on this. We're not looking for perfection. This is a complete drawing packet where I have actually taken out some of the parts that you guys are going to be required to dimension. I don't want to show their answers for that, but I just want to go through and show maybe where these views are helpful. So this was the student's version of this is their first drawing in the packet. This was their full assembly in its entirety. And pause me for a moment and think about, just scan the page here and think about whether this is complete. Okay, this is pretty close, right? It's a good looking assembly. That's a great view of it. I've got my parts table, but the one thing that's missing is I don't have call outs, right? So I don't have call outs that are saying, hey, 1 shooter body, right? 5 trigger is this guy, chamber is 3, right? So that would still be needed. Every single assembly drawing that you're putting up there needs to have those part call outs and the part table, okay? The other thing that would be missing is that there's one piece here that we need to figure out a way to attach, and that is this barrel. So how is this barrel sitting in the body? Is it glue? Is it stapled? Okay, so you'd have to make a decision as an engineer. You could decide maybe that's going to be a precision fit, but with that much of it being in there, this would still probably pop out. So you're going to need something beyond just a press fit in order to get that in there. So I would recommend either glue or staples. You can pick either one of those. I believe the rubber band shooter that I have actually uses staples, not glue, but you would just have a call out for that, right? Okay. Next up, we have our exploded assembly. Put me on pause and think about whether this is complete. Right, this is also pretty good, right? So this very clearly shows how things are going to come together. The one thing that is missing, though, is it would be helpful to have exploded assembly lines in there. Okay, so the lines that go back to the origin of where these parts are. Okay, so that would be helpful. But they do have the part numbers on there. That's great. Okay, but they're missing those exploded assembly lines. All right, next up we have a broken out section view. Okay, so put me on pause and think about whether this is complete. All right, this was a really great addition. So if you go assembly, exploded assembly, broken out section view, this view here shows you exactly where those internal components are oriented. You're not going to get that off of the exploded assembly, and you're not going to get it off of this view. So this view is really nice to include in your packet, as they did a great job here as the third drawing. Okay, you could make it second or third, doesn't really matter, but to have that in the packet to show our folks who are manufacturing this exactly where these parts go. Now, what is missing here again is you need part callouts. So every single drawing that is an assembly, you need the part table and you also need the callouts. The other thing that probably would have been helpful is to really call out the fact that you have these held in here with pegs. There's 1, 2, 3 pegs. You would see that off of your with your part callouts. But are those press fit into those holes? Are they glued in? What's the deal? So on my rubber band shooter, which you guys have the disadvantage right now of not having it physically in front of you. Normally I would actually just give you the rubber band shooters and these two CAD files, the part files, and then tell you to go to town. Everything else you'd have to measure yourself on your rubber band shooters. If you could hold a rubber band shooter right now, or at least the ones that we're using, you would see that these are both press fit in and glued. So it's glue and a press fit to get those in there. But you would want to call that out probably on this drawing. This would be a good opportunity to talk about those pegs. What's up with the pegs? Okay, so those are our 3 assembly drawings, and this student did a good job of putting those in the right order. Again, we're missing some part callouts that need to be highlighted, some descriptors for how you're mating parts together in an assembly. Okay, you've got a couple instances where we need to call out that you want the manufacturer to put glue on there. All right, now we're going to go through and we're going to look at, or we're going to talk about the individual part drawings. So part 1 is the shooter body. I'm not going to show you this student's version of their engineering drawing for the shooter body because that's on you. I want you to create your own work, okay? But let's talk about what would need to happen here with the shooter body. So the shooter body is this piece here, okay? And it has a little interior section to it, right? There's a little bit of an interior space that's going to hold these components, okay? And it's also going to create this well for the barrel. So one thing that might be good here is to do either a broken out section view of this specific part, or you could also do a full cross section view. So if I slice this right down the middle, okay, so I took a plane and I basically sliced off this front surface, I would get a good view of this as well. So I could go with a section view or a broken out section view in addition to all the other views that you're using. So you have a front view, a top view, and a side view. You may also want to include a section view on that, okay? All right, so that would be the shooter body. Let's talk about the barrel, okay? So that's this piece right here, okay? Think for a sec, do you need any additional views for the barrel? The barrel really doesn't have, it's not that complicated of a part. That might be a part that I would have asked you to model maybe in your first or second week of using SolidWorks, right? So there's really nothing that's going to be complicated about that. So I would expect a straightforward engineering drawing for your barrel. All right, so we're talking front view, top view, side view, and an orthographic projection, and then making sure you have your dimensions on there. But I don't see a need for a section view or a detailed view there. Next part in our list, so part number 3 is actually the drawing that I provided to you. Okay, so this would be for the chamber. Okay, and you notice that for the chamber, what we have here is we've got a front view, and then we've got a section view instead of a top view. That is totally legit. Okay, front view and section view. Okay, and then what we have to communicate the detail here is a detailed view in the right corner instead of an orthographic projection. You have a little bit of leeway with more complex parts when you're trying to fit them onto one page like this to kind of break away from, some of the standards that we've conveyed, right? So far in the class we've said front view, top view, side view, then an isometric in the top right hand corner. You can never do anything but that. In this type of part, right, it can be conveyed pretty clearly from the front view that this is just going to have a little thickness to it. So an isometric wouldn't tell us much more than the front view and the section view together. And I'm going to use the space that I normally would have held for the isometric for my detailed view. So this would be a legit way to do this. Okay. Next up, we've got our pegs. Okay, think for a sec about the pegs. Anything special about that? The answer there is definitely no. Okay, the pegs are just little cylinders with blunted ends to them. Okay, the only thing there that you're going to want to remember, okay, again, we're looking for on each drawing in the title block, we should see a material and then we should also see a quantity. So remember that you're going to need 3 of these pegs in your design. Okay, and last but not least, we have our trigger. Okay, so the trigger is, I would expect to see something that is going to be comparable in detail and complexity to the chamber. Okay, so you may need for the trigger a detailed view, okay, to convey maybe what's going on up here at this little beak that's happening. Okay, that beak is super important. It moves back in and stops the wheel from advancing. You've got rubber bands that are going to want to pull this wheel forward if you're shooting multiple rubber bands at once. So this little mechanism kind of ratchets back and forth as how it functions. Okay, so I would expect maybe a detailed view to help with that, similar again to what we did here, okay, for the chamber. All right, so that's going to be the doozy, folks, is giving us that that engineering drawing for the trigger. Okay, with the trigger, this is also a good time to talk about some advanced dimensioning practices that we're not going to cover in this class. Okay, so again, I'm not going to make you do these dimensioning practices. Our hope is that in a year or two, we will have a second CAD class that will be advanced manufacturing and CAD, where you would get into some of these more detailed practices. Some of these practices are especially useful in high-tech manufacturing. Okay, so when you've got manufacturing that needs to be super, super precise, like aerospace or military, okay, or medical devices, use those types of practices. All right, so another practice that may be useful for dimensioning the trigger, I don't expect you to do this, I expect a standard dimensioning practice like we've been covering in class, is something called a coordinate dimension. So coordinate dimensions can be helpful when you've got really complex curves, okay, so that trigger has some interesting curves on it. So here would be a curved surface, okay, this is just an example here. Here would be a curved surface, so that curved line that goes around here, I don't know, maybe it's a fin on a fan or something like that. It's got a really interesting curve to it. Okay, that's put together as what we call a spline. So there are points in space that you're interpolating with a polynomial curve. That's what a spline is. Okay, and those points that are being used, these individual points, are laid out as markers, right? So we've got points in space, and you're basically dimensioning. We've got all these nested dimensions trying to locate that. This is a rat's nest of dimensions. So this is standard dimensional practice, standard practice for calling out dimensions like we've been using in class. Now, coordinate dimensioning basically says, okay, instead of having all those leader lines and everything else, what I'm going to do is I'm just going to have a point in space, okay, and then I'm going to list its x and its y value relative to a coordinate system that I put on the drawing. This coordinate, this 0 point, can be on the part, it can be located on the part, or like shown here, it could be off of the part, and your points are going to come up in space. Okay, so so this is kind of the guts of coordinate dimensioning. Okay, is basically to locate points in XY space. Okay, rather than having a bunch of leader lines, and you would do that to prevent this kind of situation where it's really actually hard to tell what you're even dimensioning because of the number of lines that are on there. So that's your minute introduction to coordinate dimensioning. Again, I'm not expecting you to do this, but if you see this out there, this is it's something you can understand, right? So I mean, it's pretty intuitive given your training as an engineer thus far, that this would be referring to these points in space. Those would be coordinates in x and y. Okay. All right. The other dimensioning practice, and this is actually a dimensioning and a tolerancing practice that you may encounter, and that we're saving for our advanced CAD class, which will hopefully be online in a year or two, is something called geometric dimensioning and tolerancing, GD&T. Okay, again, this is a practice that you will encounter in high-tech fields where parts need to be exceptionally precise. So aerospace, military, medicine, okay, you would encounter these types of this practice, geometric dimensioning and tolerancing. Okay, so we have dealt with standard tolerancing thus far, tolerancing to achieve a particular engineering fit, right? That has to do with holding basically one dimension, okay, or maybe two dimensions within a specific range. GD&T covers holding actual shapes to a certain shape. So how circular is your circle, let's say? How square is your square? How flat is your line? How perpendicular are two lines to each other? So that's basically what these designations mean. So this guy here, okay, this perpendicular, is calling out basically that the long axis of this cylindrical hole is going to be perpendicular to the rest of the part within a certain dimension. Okay, you also have dimensions for flatness, perpendicularity, circularity, all of that. Okay, how you can tell if a design or a drawing that has GD&T is sort of, I want you to be able to just recognize that if you see something that looks like this, okay, you see all these boxes with these symbols in it, okay, that is going to be GD&T. Okay, so that means that you're probably dealing with a highly precise part where just holding to standard tolerancing, where you're saying, okay, this dimension has to be within 1/1000th of an inch. That's not enough. You need something else to make that part work. You need to deal with the flatness of surfaces, perpendicularity of surfaces, etc., etc. We're going to reserve further discussion about this for the later course if you're interested in it. This is also something that we've heard from our alumni that they do get an orientation to on the job. Is if the field that you're working in requires this level of tolerancing, you may learn it on the job as well, but hopefully we'll have a course where you can learn it in detail too. Okay, GD&T. All right. So with that, I'm going to do a hard pivot, folks, over to your design project. So this is the last bit of the class that we're going to cover today, is your design project. First, I want to start with reminding everybody where we are. Okay, so we are nearing the finish. We're week 10 going into 11 here. Actually, we're solidly in 11. Okay, and we're dealing with phase 3. So our engineering design, detailed engineering design. You guys are pulling together drawing packets for your design. What's coming next is we're going to briefly do design validation. Obviously, you are not going to be able to test your actual prototype because we don't have you on campus to build your actual prototype, but we're going to show you how to perform some calculations and also how to use SolidWorks to do some degree of design validation. So that's what's going to come up next after next week. So next week will be our exam week. The following 2 weeks after that are going to be dedicated to design validation and getting ready for our final showcase. So it will be a virtual showcase. It'll be an online showcase. You guys are going to have a presentation that you're going to do to a panel of judges, including some faculty and your TAs. That'll be done over Zoom, so you'll actually be given controls to do the presentations on Zoom yourself, and you're going to show off your designs. And there'll be more coaching on that in this class, and then we're also going to cover how to put together presentations in MEEG104, which will be super useful for this class as well. Okay, so that's what's coming. I do want to apologize. We are about a week, 2 weeks late on your first peer evaluation. We're experiencing some technical difficulties with CAPME, but we hope that we get it resolved this week and we'll have that launched. You will have this interim CAPME, so we're having this kind of, let's say, 2/3 of the way through CAPME, and then you will have a final CAPME. The 2/3 of the way through CAPME, look for more information on that. It is going to apply to some of the milestones earlier in the course, but what we're basically using it for is to really do an intervention if your team isn't functioning well. Okay, so sorry that's come a little late, but we will have a 2 CAPMEs, one hopefully towards the end of this week, and then or the beginning of next, and then one definitely at the end where you'll have a chance to give feedback on the functionality of your team. Okay, so that is sort of the overview of what's coming up on your design project. This is a good time to talk about one particular issue in your design project that relates very closely to phase 3 detailed design, and that is toy safety. Okay, so your toy designs need to be safe. They need to be safe. That is a constraint that they are safe. Okay, so I want to start by thinking a little bit about, and some of these slides I have covered in an optional video that I posted earlier in the class. Some of these are new, okay, but it's a chance to refresh all of our memories that we are really concerned about toy safety. So toys are super fun, but kids can also get hurt with them. Kids are also very destructive with toys. Okay, so this is my niece, circa, God, about 2 years ago now, 3 years ago now. There's now a new one that looks just like her. Okay, they could be twins. But this is Macy. We call her the Moo. Okay, Macy Moo. This is actually my pool toy that I made years ago. Okay, and she's playing with it. She's giving us some feedback. But you could think about how a kid might hurt themselves with a toy. So something as simple as Macy there with the pool toy. How could she get hurt by this? So let's kind of go through the list, all right? So one is chemical ingestion, paint, all right? So we are making sure that any painted surfaces, and you should note this on your drawings, are finished in acrylic, okay? They're not finished in any oil-based paints or any paints with nasty chemicals, okay? The other is they could cut themselves, all right? So a kid could cut themselves on a sharp surface. They could swallow a small part, okay? So actually this toy I would be concerned about, this is a cactus, I would be concerned about these little balls coming off and then Macy being tempted to eat them, okay? They could break it and then swallow a small part, okay? So that would be the instance of those balls coming off. They could hurt themselves with the cord, okay, right? So that cord could get wrapped around them in some way. They could also, let's talk about breaking it. How could a kid break this down into parts that could be eaten or parts that would then be sharp and they could cut themselves? Well, Macy could sit or stomp on it. That would be very likely. Okay, throw it, drop it, bend it, twist it, pull it, or crush it. Okay, so kids do all of these, right? Kids are going to be rough with your toys, and we'll get into a test that looks at that in a second. Okay, so there's all different ways that they could do this, and this is a picture from about a year later. So they also do this with real live toys. This is my beloved cat who's no longer with us, but she was very tolerant of pulling, bending, and twisting, and did not scream at the kids. So there's my niece and nephew and my daughter there, and the beloved cat. I couldn't get rid of this shot, but anyway. Okay, so ASTM Toy Safety Standard is what we use to ensure that toy products are safe. This standard is lengthy. I have provided you with the entire standard. Okay, I'll make sure that it's also uploaded with today's workshop, but it has forever been in the resources section on Canvas, Files, Resources. You'll find this document in its entirety. This is not a document actually that you can just download online. Okay, you have to pay for these. University of Delaware has a subscription to ASTM, so we're able to get these standards. But this like bazillion page document is basically everything you need to know about safely designing a toy. And in order to have your toy product marketed and sold in the United States, the toys that you're making need to actually pass this standard. Okay, so there are several tests in here. There's a bazillion tests in here, but the three biggies are the use and abuse test. So this is basically how a kid is going to beat up your toy. The second is the sharp edge test, okay, making sure that they don't cut themselves. And the third is the small parts test, making sure that they don't choke on a small part. Okay, those are the three big ones. Then there are a bazillion design-specific tests. Okay, these are for things like if you have a cord. Okay, so that pool toy I showed before, you'd be worried about the cord. Okay, cord length needs to be regulated. Magnets, I've heard that some people want to include magnets in their designs. That's great, but there are specific regulations around magnets. There's everything. Pool, P-O-O-L toys, okay? Rubber projectiles, okay, you're going to see all of that in here. So if your toy has a specific way that a kid could potentially get hurt, chances are it has been documented and regulated in this standard. So let's focus on the big three to start off with, because those are going to apply to all toy designs. All your toy designs need to pass these three standards. You need to show us some evidence in design validation that they are going to pass those standards. Okay, if we were in person, we actually have the resources to do this testing, so we would do the testing for you. But what we're going to do instead, now that we're online, is you're going to virtually basically show that you think that your toy is going to pass those standards. Okay, so let's start with use and abuse testing. So for use and abuse testing, the big bit of information is Table 5. So Table 5 from the standards, you're going to see a table that looks like this. Okay, there are 5 different tests. They don't always all apply to your particular toy design, but one that always is going to be the drop test. Drop test, torque test, tension test, compression test, flexure test. So it's basically dropping the toy and then twisting, bending, or squishing it, okay, or pulling on it are the other ones, all right? So let's just focus on the drop test for a moment. What needs to happen with your toy to pass the drop test? Well, if your toy was intended for kids over 3 years of age, okay, so it's stratified by age. So let's start down here, 3 years to 96 months, okay? So you would need to pass, your toy would need to survive a drop of four drops from 3 feet. 3-foot drop, 4 drops. Okay, you would need to drop it onto a hard surface. So the floor needs to be, I think they actually specify they want linoleum. Okay, but basically dropping your toy from a 3-foot height 4 times. Interestingly, you'll notice that for a 0 to 18-month-old, they actually want 10 drops from 4.5 feet. Why do you think that is? Why is that standard harder for little kids? Well, if you've ever encountered a little kid, a 0 to 18-month-old, you know that they drop things all the time, okay, frequently from high chairs. So this additional 1.5 feet is to accommodate a drop from a high chair, not just the height of the kid, and they're going to drop it a lot, so they want 10 times. Okay, so what happens is, what is a pass for the test? All right, a pass for the test is if I drop this toy and it doesn't break at all, great. If it does break, because sometimes things are going to break, right? So if your toy does break, it cannot produce pieces that are small enough for a kid to choke on or have sharp edges where they could get cut. So your toy can actually pass even if it breaks. I mean, obviously the ideal condition is that you drop it and it doesn't break. But if your toy breaks when it drops, it cannot produce parts. It would still pass this test if it only produced parts that were too big to choke on and too dull to cut yourself. Okay, and that is the standard that everything else goes by too. So the tension test, let's say, let's look at that same age range, 36 to 96 months, would need to stand up to 15 pounds of tension. So I'm pulling on my toy with 15 pounds. Okay, and if I do that, if it doesn't break, great. If it does break, I could still pass the test if I'm not producing parts that are super small or super sharp. Okay, so what do we mean by, let's start with super sharp. Okay, so super sharp means that a kid could cut their skin with it. Okay, if they ran their finger along the edge of the part or gripped it, they could potentially cut their skin. Believe it or not, there is a test for this as well, and it uses a little test setup. We have a version of this, a homemade version of this in the design studio. But basically what it is it's a little spindle that rotates very slowly, and there's an applied downward force put on it. You then put your part, so in this instance, this little block is what the part is, up against that spindle. The spindle's coated in one layer of, we use actually PVC plumbing tape, okay, so that little plumber's tape that you use to make sure that your valves don't leak. Okay, we would run one coating of that around this, and if this part does not cut that tape, you basically would not cut a kid's skin. Okay, so that would be the sharp edge test. Virtually the best way to check for a sharp edge test is just to make sure that any edges of your parts that would come in contact with the kid have some radius on them. They're rounded in some way. Just like for those of you who are able to do the machine shop project, you blunted the ends, you ground down the ends of your metal piece and your plastic piece to make sure they weren't sharp. You would make sure that on your drawings, your engineering drawings, you're doing the same thing here. Okay, so that would be the sharp edge test. Again, this is for parts as they are, okay, on your drawing, so your intact design. It's also, this same test needs to be rechecked if your parts would break apart during use and abuse testing. So if a kid drops it and your design breaks into two, you just need to check that those pieces don't then fail the sharp edge test. Okay, the other big test is what's called the small parts test. So the small parts test, it fits a certain age group, so I think it's 36 months, 3 or younger. Okay, so you'll see a lot of toys are ages 4 plus. Okay, that's because under that age, you have to pass a small parts test. So things like Legos, okay, are designed for older kids because younger kids have a tendency to swallow them. Legos are actually quite risky if you've got them with a crawling baby or even a toddler, because they could swallow them and it could actually lodge in their esophagus. So the test for this is actually you have to, there's a specific little device, okay, it's called a small part cylinder. We have these in the design studio. They're very cheap. If you don't have a small part cylinder, you can actually use a toilet paper tube, okay, is a pretty good approximation of the size of a child's esophagus. So this is meant to simulate the size and depth of a kid's esophagus. Okay, 1.25 inches inner diameter, and a depth, it goes from 1 inch to 2.5 inches. Okay, so if a part fits completely in this space, so I plunk it into this tester and it fits completely in this space, it is too small to use for kids who are under the age of 3, I think it is. Okay, if the part extends out from this space, so it's peeking out of this window, so I plunk it in here, but the top of it's peeking out. That does not fail the small parts test, okay? So what could happen there is a parent or somebody could see that a kid is trying to shove this thing into their mouth. They could grip it and pull it back out. And then obviously there are some parts that just aren't going to fit in here whatsoever. They wouldn't even fit into this interior chamber, and those would be fine. Those would pass the small parts test. Again, with the small parts test, so this is applicable to younger age kids, okay? You would need your design to pass it in its intact form. And then if your design breaks during use and abuse testing, you would need to retest any parts that are produced, any small fragments that are produced, and make sure that it passes the small parts test. Okay, so those are the 3 major tests. There are some design-specific tests and guidelines that you should be aware of, and we expect you to follow if your toy design that you're coming up with has a particular way that a kid could get hurt that is not covered by use and abuse, the sharp edge, and the small parts. Okay, so 2 examples of this. First, if your design has a lot of freestanding cord straps or elastics, you should be aware of the cord strangulation test. So basically, your cord has to have a certain length to it. And there's something called a head probe that is used quite frequently. So basically, the cord has to not be able to wrap around a kid's head or neck. Okay, so check out section 414 of the standard to figure out what the lengths of your cords or straps would need to be. This is also age group specific, so older kids can get away with longer cords. Okay. Magnets. So I've heard a lot of people talking about magnets. Okay, there are regulations on magnets. You want to check section 438. Okay, the biggest one is basically up to 14 years of age. You don't want any free floating magnets. So you don't want a high strength magnet that's just kind of loose in your toy. You want it to be embedded into the part, and you want to make sure that it never comes loose during regular use and abuse testing. Okay, but check out section 438 for magnets if you're thinking about magnets. So I want to remind you again that it is a constraint that your toy design meets ASTM Toy Safety Standards. Okay, so required for your toy are going to be the use and abuse test. We're going to discuss in 2 weeks, so after next week's exam preparation, the following week we're going to get into how to validate your design for use and abuse testing. The sharp edge test, you can start validating that right now, actually, at least for the intact parts. You want to make sure that all edges are blunted. So if you're working on your design in SolidWorks, make sure that any parts that would come in contact with the user are blunted, they're radiused or they're chamfered. Okay. The small parts test, again, you can look on your intact design if you have removable pieces that are intended for younger age ranges, okay, that would fail the small parts test. You may want to think about resizing them. Okay, so you can use SolidWorks right now to take care of sharp edge and small parts, at least for the intact design, and then we'll talk about use and abuse testing in 2 weeks. All right, design specific. Okay, so again, now's the time to think about what else am I including in my design that a kid could get hurt on that may be covered by the ASTM Toy Safety Standard. Okay, you want to note any features that have safety concerns beyond those addressed above: cords, magnets, projectiles, bath toys, okay, all of that. All right, and then you want to research the safety guidelines in the ASTM safety document. Okay, so this is your chance to go into that document. Please don't feel like you need to read it in its entirety. It's like 90 pages long. Okay, but you can do a word search. It also has a great index at the beginning that will help you find certain sections. So if you've got, a projectile, just search for the word projectile and see what is going to come up there. Okay, and that would be an additional guideline that you need to work with. All right, last slide here. I just want to remind everybody that midterm exam number 2 is going to be Thursday, April 30th. So that's next week. From the exam period itself will be the standard 75-minute class period, 9:30 to 10:45 a.m., although we'll have check-in 15 minutes before, and it typically takes 15 more minutes to check out. So if you have a class right before or right after, now would be a good time to let that other professor know if they're doing synchronous classes that you may need to skip out a little early or join a little late. It'll be proctored via Zoom, just like last time. That went well. We'll do it again. Okay, review materials are posted. They'll be posted today. The next class, so Tuesday's class, the 28th of April, will be dedicated to exam review, but I'd highly recommend that you start before then, okay? I'd like you to check in if you're taking advantage of DSS. Please check in with DSS now, and we will make sure that you have a special proctored session, okay? But those are your reminders for the exam. Thanks for tuning in, and we'll talk again hopefully during our optional discussion sections, but definitely next Tuesday.